Hi friends and my dear students, welcome back once again to my class. Today, let us learn something very important from the exam point of view, and that is locating tetrahedral voids and octahedral voids. Okay, this is very important topic because you can expect questions for both your board exams as well as competitive exams. So friends, please be with me throughout this video. But before we look into the details of this topic, I request you to watch my previous video where I had elaborately explained about close packed structures. Okay, that is either CCP or HCP type. CCP stands for, just try to recall, cubic close packed, and HCP for hexagonal close packed, isn't it? So this particular topic has the link with the previous topic. Please do watch the video and then get back to this topic. Fine, guys? Okay, now let's begin. So in the previous video, we saw, in fact, that close packed structures, either CCP or HCP, right, will have two types of voids. That is empty spaces. What are they? Tetrahedral voids and octahedral voids. In short, we have simplified it as TV and OV accordingly. Okay, so throughout our discussion, I'll be mentioning as TV and OV, so don't get confused. Okay, guys. So now that we know whether CCP or HCP contains both types of voids, the next obvious question that should arise in your mind should be this, I hope, and that is, how many voids are present, ma'am? How many TVs are present? And how many OVs are present, isn't it? To understand this, try to recall. I made one statement in my previous video that the number of these voids, either TV or OV, in fact depends on the number of spheres present in these structures. Okay, this is a most important statement. So let me recall once again for you. Number of voids present depends on the number of spheres. So what is the relationship between these two? Let's look at it now. Okay. Yes. For that, yes, once again, let's take up CCP or HCP and assume that there are n number of spheres. Okay. But guys, it is very important now. Actually, it is found that the number of octahedral voids, right, either in CCP or HCP is also n. That means what? The number of octahedral voids and spheres are equal to each other. This is very important. But whereas the number of tetrahedral voids, yes, it is found to be equal to 2 times n. That is, it is twice the number of spheres present. But here, number of spheres and number of octahedral voids are equal to each other. That means it follows that number of TV should be twice the number of OV also. Therefore, we get two important relationships. What are they? Number of tetrahedral voids is always equal to 2 times the number of spheres present. At the same time, number of TV is equal to 2 times OV. 2 into OV. Now let us try to prove this relationship. Why should we know this? Yeah. Once you remember this, okay, it will be easy for you to solve certain numericals. Therefore, don't by heart this. You have to understand this. To understand this mathematical relationship, we need to first locate the TVs and OVs. That is, tetrahedral voids and octahedral voids. For that, let us take up CCP, right? That is FCC type of unit cell, and continue our discussion, okay? Because it applies for CCP as well as HCP. So we will take up CCP. Fine, guys? Okay, let's begin now. Yes. So we have considered FCC unit cell, and here we are trying to locate what? Tetrahedral voids and octahedral voids. To begin with, let us start locating tetrahedral voids. Fine. For that, you need to take up the FCC unit cell. Is this FCC unit cell? Absolutely not. Because what is FCC unit cell? Look, the particles should be present at the corner positions as well as at the centers of the faces. How many faces are there? 6 faces, we know that. So at the center of each of the face, look here, 1, 2, 3, 4, 5, 6. You have 6 face-centered spheres. At the same time, you have 8 at the corners, right? Look. So this is your FCC unit cell. Convinced? Okay. But if you watch carefully, in this FCC unit cell, right, can you see 8 small cubes? Because this entire unit cell is actually subdivided into 8 small cubes. Look here. 4 at the bottom layer and 4 at the top layer. And in each small cube, if you observe carefully, there are only 4 spheres. Where are they? 1 at the corner and 3, right? Let me show in a different color pen. Let's take red. So here you have, I'll put it into mark, 1 at the corner, these 3 at the face centers. Yes or no? These 4 belong to this small cube in the bottom layer facing us, okay, towards the front. Are you clear? Now, why am I very particular about these spheres? Because I want to see the space, that is the empty space within these spheres pertaining to one small cube. For that, if you have to look at the space, we have to join all these. Then only we get a closed structure. So let us join all these 4 spheres, okay, by drawing the lines. So I think now you got it. This is a regular tetrahedron, isn't it? So that means the space within that tetrahedron represents the tetrahedral void, because void is an empty space. Are you clear? That means, friends, here in every small cube there is one tetrahedral void. Now let's go ahead. So number of tetrahedral voids in each small cube. Just now we saw. How many we saw? Only 1, isn't it? 1 we saw. That's here. But how many such small cubes are there? 8, isn't it? Good. That means if there is one tetrahedral void in each small cube and there are 8 such small cubes, obviously the number of tetrahedral voids in this FCC unit cell should be how much? 1 into 8. That is nothing but 8, isn't it? Okay. We are looking at the relationship between number of TV and number of spheres. So now we need to recall something here. How many spheres, or you can say constituent particles or atoms, as the case may be, right? So how many atoms are present in one FCC unit cell? In fact, I had taught this particular concept also in one of my previous videos. Please do watch. Okay. There we understood the contribution made by each and every particle because of the position it occupies, as well as we also saw how to calculate the number of atoms per unit cell. So try to recall here the number of atoms per unit cell. Which unit cell we are talking about? FCC. So the contribution made by the corner atom is 1 by 8, and the contribution made by the face centered atom is half. How many corner atoms are there? 8. So 1 by 8 into 8 will be 1, isn't it? I'm just trying to recall it for you guys so that you understand easily here. And half is the contribution made by one face-centered atom, but there are 6 such face-centered atoms. So half into 6 will be 3. So you have 1 due to exclusively the spheres at the corner positions and 3 due to the spheres at the face centers. Therefore, 1 plus 3 is 4. Okay. Actually, it is 4. Clear? 1 plus 3 is 4. Good. But the number of TVs we found is how much? 8. So we have 8 TVs and 4 spheres. So what is the mathematical relationship? Very simple. 8 is equal to 2 times 4. That's what is the relationship here. Number of TV, which is 8, equals 2 times 4 means 2 times n, because n is nothing but 4 here. What is that? Number of spheres or atoms per unit cell. Did you get it? So we proved the first relationship. Now let us look at locating octahedral voids. Fine. Okay, friends. Now let us locate the octahedral voids in the FCC unit cell. But in order to locate these voids, we should first of all find out where they are present, isn't it? Yes, they are found to be present at both body center as well as at the edge center. So now let us try to find out the number of OVs at body center to begin with. Okay. For that, take a look at our FCC unit cell once again. Fine. So where is the body center here? Don't you think this particular point represents the body center? Yes. But at that point, you don't see any sphere being occupied, isn't it? Yes. So the body center, though it is not occupied by any sphere, but it is surrounded by 6 spheres, right? One at the center of each face, correct? That is these. Around this, right? So let us join all these spheres at the face centers. Look, did you get a regular octahedron? And this is the circle that actually denotes the body center. Fine. So this is a closed figure octahedron. We know that. That means it's enclosing a space within. It's an empty space. That empty space obviously represents the octahedral void. Okay, that means how many octahedral voids are present around this body center? It should be 1. Why? Because the body center exclusively belongs to one unit cell, and there is one octahedral void around that body center position. Therefore, the entire octahedral void, okay, belongs completely to one unit cell only. Therefore, number of octahedral voids due to body center position is 1. Okay. Now, I told you they are present also at the edge center. So, let us now try to find out. Okay. Yes. Number of OVs at edge center. For that, let us take a look at the FCC unit cell once again. So, before we look at the edge center, first of all, you should know how many edges are present for a cube. So, let me draw a cube for you. A simple cube. Draw a square. And one more square. Okay. Join all these. Good. Okay, did we join? Now, what are the 12 edges? Right. This is 1. This is 2. This is 3, 4. The face that is at the front. Let's take up the back face. 5, 6, 7, 8. Okay, let's take up these 2 faces now. What are left out? 9, 10, 11, 12. So there are 12 edges. Please remember this. If there are 12 edges, obviously there should be 12 edge centers. That means center of each edge. Okay, keep this in mind now. Right. So, number of OVs at edge center we need to find. For that, we have to consider one particular edge center, isn't it, to begin with? Yeah. Let us take up this edge. Okay. This one. This edge. Now, where is the edge center there? Obviously, this is your edge center. Along that edge. Are you clear? Out of the 12 edges, we have considered that edge. And that is the edge center. Now, once again, this edge center is not occupied by any sphere, but it is surrounded by 6 spheres. Do you think all the 6 spheres belong to the same unit cell? No. Just take a look. Can you see? 1, right? 2, 3, and 4, right, belong to this unit cell. Whereas these two fellows, the orange spheres, just to differentiate, we have given that set. So these two belong, it is 5 and 6, to the adjacently placed unit cells. Okay, so 4 from this unit cell and 2 from the adjacent unit cells. Okay, but out of the 4, okay, 2 are at the corners and 2 are at the face centers. Clear? Very good. But when we joined all these spheres around that edge center, once again we got, yes, a regular octahedron, which is representing the octahedral void. That means, friends, there is one octahedral void at one edge center, or at each edge center. How many? Yes, here we got 1, isn't it? At each edge center, you found one octahedral void. But how many edges are present? 12 edges. So how many edge centers should be present? 12. Just now I showed you. Okay. But do you think that edge center, right, belongs to one particular unit cell exclusively? Absolutely not. But whereas when we looked at the body center, I told you that position is at the center of the body of the unit cell. So it exclusively belongs to that unit cell only. Therefore, there was one octahedral void also around that body center. But here, this edge center, okay, does not completely belong to one unit cell. It is shared by the other adjacent unit cells. Therefore, the octahedral void around that edge center does not belong completely to one unit cell. Please remember this. Only a portion of it or a fraction of it alone belongs to this unit cell. Okay. For that, we should know the contribution, okay, made by the edge center now. For that, take a look at this figure. Can you see 4 cubes here, all touching each other? 2, okay, facing us and 2 at the back. Yes, all are touching each other. Yeah, and you can see that this is the common edge, the edge that is shared by all the 4 cubes. Yes or no? At that common edge, yeah, we have placed what now? A sphere at the center of that common edge, to be more precise. Okay, so this is an edge center of this common face, and at that edge center, if at all we place, okay, a sphere, I am just teaching you the contribution made by that particle when placed at the edge center. Clear? Okay. Now, this particular particle, right, is shared by 4 unit cells. Isn't it, my dear? In other words, 4 cubes. Look, 1 here, 1 at the back, 1 more there at the back, and 1 here at the front. So since this is shared by 4, what is the contribution made by one particle to one unit cell? Isn't it 1 by 4, my dear? So here we got 1. Here also we got 1 at each edge center. Number of edge centers is 12. Once again, I'm writing for you. Now, the contribution made by each edge center should be 1 by 4, because one particle is shared by 4 cubes. Therefore, how much of that particle belongs to one cube? That will be obviously 1/4. Okay, very good. Let's proceed. Therefore, my dear friends, number of OV at edge center per unit cell. How will you calculate this? Very good. Since the contribution made by each edge center is 1/4, and we found 1 OV at each edge center, what is the meaning? Connect between the two. That means only 1/4 portion of the OV will belong to one unit cell. Is it very clear? Due to one edge center. But there are 12 edge centers. Therefore, the total number of OVs at all the edge centers per unit cell will be obviously 12 into 1 by 4. That is 3. Did you understand? Yes. So let us write 3 here. Okay. Therefore, friends, total number of OVs, okay, now due to body center and edge center will be how much? 1 plus 3. That is 4. Once we have found out the number of OVs per unit cell, we need to connect it to the number of spheres. Yes. How many spheres are present in FCC unit cell? Just now I taught it is 4 again, isn't it? That means it's very, very clear that number of OVs and number of spheres are both equal to each other. That is 4. Okay. And how many spheres are present in one FCC unit cell? 4, isn't it? We just now saw that. Therefore, friends, we got 4 OVs and we also saw 4 spheres per unit cell. That means number of OVs and number of spheres are both equal to each other, and that is found to be 4. Therefore, we can conclude like this. Number of OVs is also equal to number of spheres, means we consider spheres to be n, isn't it? Therefore, number of OVs is n, and number of TV we already proved it is 2 times n, and number of TV now we can prove if it is 2 times n and number of OVs being same, in place of n we can put OV. That means number of TVs will be equal to twice the number of OVs. Okay. So we have successfully proved the relationship between number of TVs and spheres, and number of TVs and number of OVs, and number of OVs and number of spheres. But what is the significance behind all these relationships? Yes, if you know these relationships, you can actually find out the formula of a compound. Let us consider an ionic solid, okay, as an example. And we know ionic solids are made up of, yes, oppositely charged ions, that is anions and cations. And I hope you remember that anions are relatively bigger than the cations. As the anions are bigger, right, they tend to occupy the lattice sites or lattice points. Whereas the cations being smaller, right, they occupy the empty spaces or the voids. And we know there are 2 kinds of voids, TV and OV. Now, then the question arises, right, when will TV be occupied, or when will OV be occupied, right? Yes, the same cations, if they are small enough, then they try to fit into the TV, which is a smaller one. But if they are slightly bigger, out of the cations also you can have relatively bigger cations, then those type of relatively bigger cations prefer OV because it's a bigger space than TV, isn't it? So friends, we can conclude like this. Not all TVs and OVs are completely filled. Instead, so we can conclude like this. Not all TVs and OVs are completely occupied, but actually only a fraction of the OV or TV get occupied. And that fraction, okay, of the OV or TV that is occupied in a given compound, in fact, depends on the chemical formula of the compound. Okay, so let us prove this by taking up certain numericals now. Are you ready? Okay, shall we look at the very first question? Yes, it is picked up from NCERT example 1.1, and the question goes like this. A compound is formed by 2 elements X and Y. Atoms of element Y as anions make CCP, and those of element X as cations occupy all the octahedral voids. The question is, what is the formula of the compound? So, yes, it's given that a compound is formed by 2 elements X and Y. So, to arrive at the formula, first of all, we should know the type of elements present. It is X and Y. And now we need to find the number of atoms of X and number of atoms of Y and find out the simple ratio that exists between them. For that, let us look at the data once again. It's given that atoms of element Y as anions make CCP. That means it's occupying the lattice points. Just now we saw that number of spheres is n, and these spheres will be present at the lattice points, and it is given that atoms of element Y make up CCP. That means the atoms of element Y are present at the lattice points, which in turn is equal to number of atoms. That means number of atoms of Y as per our assumption is n. Okay, good. And those of element X as cations, just now we saw cations occupy the voids. Which void here? Octahedral voids. And we also know the relationship between number of octahedral voids and the number of spheres. What is it? Just now we saw, yes, number of OV and number of spheres. Both are equal, isn't it? So this is also equal to n. And at OV, what is present? X. So it follows that number of atoms of X, that is occupying the OV, should be now equal to n. So number of atoms of Y, we found n. You take the ratio between X and Y. Number of atoms of X also is n, isn't it? So n is to n means what? It's nothing but 1 is to 1. Therefore, the formula is very simple, xy. Okay? Did you understand? Shall we take up the next question now? Yes. This is taken up from NCERT example 1.2. And look at the question. Atoms of element B form HCP lattice, and those of element A occupy 2/3 of tetrahedral voids. The question once again is, what is the formula of the compound formed by these elements A and B? Okay, so the compound is formed, okay, of two elements A and B, isn't it? And once again, let us calculate the number of atoms of A and number of atoms of B and find out the simple ratio that exists between them. Okay, atoms of element B form HCP lattice. That means what? Number of atoms of B is n, isn't it? Because HCP lattice means lattice points, in other words, right? And lattice points means you should always take it as number of spheres, because at each lattice point there is one sphere present. That you know by now. Therefore, since atoms of B is occupying the HCP lattice, it's understood that number of atoms of B is n. Clear? Now, number of atoms of A, right, occupy 2/3 of the tetrahedral voids. Just now we saw that either TV or OV, for that matter, will not be completely occupied. Only a fraction will be occupied, and the fraction of either TV or OV occupied in turn depends on the formula of the compound, isn't it? Now see, the same concept is coming up once again here. 2/3 of TV only is occupied. But actually, we know, as per the relationship we just now saw, number of TV is actually twice the number of spheres, that is 2n. This is the relationship just now we saw. But though 2n, okay, TVs are available, but still it is given that the element A occupies 2/3 only. So actually, how many TVs are occupied now? Yes. Number of TVs occupied will be 2/3 of 2n, because 2n is actually present, but not the entire 2n is occupied, only 2/3 is occupied. Therefore, it will be 2/3 into 2n. That is nothing but 4/3n. And what is occupying the TV? This element A. So 4/3n is nothing but what now? Number of atoms of A, isn't it? Yes. Therefore, we got number of atoms of B as n and number of atoms of A as 4/3n. So, if you take the ratio, A is 4/3, n is to n. So, cancelling out n, we have 4/3 is to 1. The simple ratio will be 4:3, isn't it? Therefore, the formula is A4B3. Did you understand? Good. Okay, friends. Hope you're very clear with the concepts taught until now. But these two problems are not enough. Okay, please practice some more problems so that you get a better grip on this concept. Welcome back. Let's take up some questions on the next topic, that is location of tetrahedral voids and octahedral voids. Okay, let's look at the first question. Yeah, the first question reads like this. A compound forms hexagonal close-packed structure. It is HCP. It's the first data you should know. What is the total number of voids? What are the different voids we know? Yes, TV, tetrahedral voids, and octahedral voids. Total means you have to add them both. So this is what they're asking. What's the total number of voids? In how much? 0.5 moles. So number of moles N is given as 0.5 mole. Okay. How many of these are tetrahedral voids? So they're asking how many are tetrahedral voids also. So let us say TV plus OV is X now. Okay. So once you find X, you can find TV. How? Very simple. TV will be now equal to X minus OV. So this is what is the procedure or the approach. So since it forms a hexagonal close-packed structure, it will have n number of lattice sites, right, where these atoms or the constant particles occupy. Okay, so let us say this contains n, right, lattice points. Where you have the constant particles. It can be ions, atoms, or if any type of molecule also. Okay, now to find TV and OV, we have to use our formula. Remember what's the formula? We know TV is equal to 2 times N and OV is equal to N. Please watch my video where I've taught you in detail how to locate the TV and OV and what is the logic behind these mathematical relationships. Without that, it's very difficult, my dear. Please watch, understand the concept, recall once, and then get back. Then there will be a smile on your face. You will be actually excited to work out these problems, and you'll be very happy at the end of the problem when you get the right answer. Please, this is my experience. Take it, okay? Personally, I'm telling you, please follow this, okay? So let's now go ahead. Those who are confident in the concept will retain a smile. I can see that smile on your face. Okay. Now, to find TV and OV, yeah, 2n formula we know, but we have to find n, isn't it? So the first thing is, what is n? Okay, to find n, can we use the number of moles? What is n? Number of lattice points at which the constant particles are present. Let us say atoms only. We'll consider them as atoms. Okay, now 0.5 moles. Yeah, in 0.5 moles, how many atoms are there? Before that, in 1 mole, how many are there? As per definition, 1 mole contains Avogadro number. Let's take it as 6.023 into 10 power 23 atoms, right? But given as 0.5, in other words, half of it, that means 6.023 into 10 power 23 by 2, isn't it? Or this entire thing into 0.5. It comes to be the same. This will be now 6.023 into 10 power 23 by 2. That will be 3.0, 2 ones are 2 and 5. You can take it as, because 2 ones are 2 and 1 remaining, you can take it as, yeah. So this is into 10 power 23. What is this actually? N. Once you know N, it's easy to find TV, right? What is TV now? Okay, we'll just substitute in place of N. Yeah. So it is 2 into this. Okay. What is 2 into this? It's nothing but Avogadro number, isn't it? Yeah, so we'll write TV directly as Avogadro number now. Yeah. Okay. So this is 6.023 into 10 power 23, and this is n. What is n? OV also. So let's write n here. I mean, substitute the value of n here. So this will be now 3.0115 into 10 power 23. We can add these two values, right? So that will come to, yeah, 5, 3 plus 1, 4, 3, 0.9, right? 3 plus 1, 4, 2 plus 1, 3, yeah. So into 10 power 23. What is this? This is total. So our x we got. What is x? X is 9 point, I'll take one more color, 9.0345. So you can make it as 5 into 10 power 23. And the TV, just now we got, yeah, Avogadro number. That is 6.023 into 10 power 23. Even if you take this minus n, you'll get the same thing. Okay, fine. So this is the answer. This is the answer. This question has been picked up from NCERT in-text series, question number 1.15. No options, so I showed you the entire solution. So please make a note of this, okay? Shall we take up the next question now? Yeah. A compound is formed by two elements M and N. So what are the two elements now? M and N. Okay. We have M and N. The element N forms CCP. So N forms CCP. This cubic close packed structure. And atoms of M occupy 1/3 of TV. So M is at TV, that too 1/3 of TV. What's the formula of the compound? Yeah, so we need to find the number of atoms of M and N and take the ratio. Correct? Okay. Now N forming CCP means it is indicating the lattice points. Once again represented as N lattice points. So this N once again. And TV, how many TVs are there? Just now we saw 2 times N. But these M atoms are occupying 1/3 of TV. What is 1/3 of TV now? 1/3 of 2N, isn't it? That means 2 by 3N. What is occupying this? 2 by 3N TVs. Yeah. M, right? Therefore, this is 2 by 3 here. Take the ratio. N gets cancelled. So it is 2 by 3 is to 1. This is nothing but 2 is to 3. Correct? Therefore, the formula is M2N3. Okay, that's the right answer. And this question is once again from NCERT in text, question number 1.16. Okay. Shall we take up the next question now? Hope you made a note. Okay. The next question reads like this. This is from NEET question paper 2019. Very recent question paper. And the question goes like this. Yeah. A compound is formed by cation C. We have a cation C and anion A. This C is to A. We need to find the number of cations and number of anions. The anions form hexagonal close packed structure. So A is forming HCP. That means we need to take it as N lattice points. And the cations occupy 75% of octahedral voids. OV, that to 75%. That means 75 by 100. Nothing but 3 by 4, isn't it? 25 3s are, 25 4s are. So this is 3/4 of OV. So this is N. And we know OV is equal to N. Okay. So A is N. And C is at OV. And OV is equal to N as per the formula. And yeah, what is OV here? Therefore, N. Therefore, here we can write 3 by 4. N. Right? And that will be 3 by 4 is to 1. And that will be C3A4, isn't it? 3 by 4 is to 1 is 3 is to 4. Therefore, C3A4. So, where is the right option? Here. A, isn't it? C3A4. Don't see all other options. It will really confuse you. Be clear with the concept, work out, and then take the right answer. Okay? Because it's not a C and tick type, right? You have to work out. The next question, shall we take up? This is from AIPMT Mains 2012. And the question reads, it's a big question. Structure of a mixed oxide is cubic close packed, CCP. Mixed oxide is actually made up of A, B, and O. So we have A is to B is to O. We need to find the number of A, B, and O atoms. For that, we need to look at the data. The cubic unit cell of mixed oxide is composed of oxide ions. Okay. 1/4 of the tetrahedral voids, here is the data. 1/4 of PV are occupied by divalent metal ions. Let's not bother about the valency. Just to confuse you, they'll give more data. Is it required for us? No. We just have to look at the number. That's it. Okay. 1/4 means, yeah, we know TV is equal to 2n. So 1/4 of this means, yeah, very simple. 1/4 into 2n. That will be 2 ones are 2 twos are half n, right? Which is occupying this? A. So under A, we can directly put half n. Let's take a B now. Where is B? Yeah. And the octahedral voids are occupied by monovalent metal B. So octahedral voids we know is equal to N. It's occupied by B. Okay. So B is how much now? Before that, O. The cubic unit cell of mixed oxide is composed of oxide ion. That means CCP. Lattice points are occupied by O. And that is number of lattice points N. That's the assumption we know. So here OV is also N. This is also N. B is N because B is at OV, or B is occupying OV rather. Therefore, this is now half. If you cancel off N is to 1 is to 1. That is nothing but what? It is 1 is to 2 is to 2, isn't it? Therefore, the right answer will be A1, B2, O is also 2. This is the right answer. Where is it, my dear? A1, B2, O2. Isn't it B? Yeah, here. A1, B2, O2. Did you understand? Okay, then please make a note. Let's go to the next question now. The total number of octahedral void or voids, because the option is 1 also here, per atom present in a cubic close-packed structure is. This is picked up from IIT 2014 question paper, and the options are 2, 4, 1, 3. Total number of octahedral voids, okay, in a cubic close-packed structure. So first of all, we know cubic close-packed structure is nothing but of the FCC type, right? Okay. And we also know that number of OV is equal to N. Here N represents number of atoms also, you can say, because it's given atom, right? Yeah. So N is number of atoms. Number of atoms where? In one FCC unit cell. Or you can say per. Okay. Per FCC unit cell. Right. How many? This also you know it's 4, isn't it? How? Do you remember? Yes. If I have to explain with the diagram, look. In FCC, we have atoms at the corners, right, as well as at the face centers. Yeah. So quickly let me show you the atoms. Here 1, 2, 3, 4, 5, 6, 7, 8. And at the FC, that means the face center. 1, 2, 3, 4, 5, 6. So we know the corner fellow, right, contributes 1/8 of itself. Rather, 1/8 of the atom belongs to one unit cell. So there are 8 such atoms. So 1/8 into 8 is 1 plus this at corners plus face center. The contribution is half, right? Okay. Half into 6 is equal to 3. So if you add 1 plus 3, you get 4. Yes or no? Okay. Be more precise. Right. So number of atoms is 4 now. Therefore, OV is also 4. That means answer 4. Look here. Number of atoms 4. OV is 4. That means there are 4 OVs for 4 atoms. But the question is OVs per atom. That means for one atom. So how many OVs will be there in one atom? Are you understanding? Then the answer must be obviously 1, isn't it? 1 into 4 by 4. It is nothing but 1. Therefore, the answer is 1, not 4. Please mark this important. Hope you understood this. So, shall we take up one more question? Okay, the next question is, yeah. A compound MPXQ has a cubic close packing arrangement of X. Its unit cell structure is shown below. The empirical formula of the compound is. This is once again from IIT question paper 2012. And there are 4 options. We don't have to look at the options. It is start solving the problem. Look at this diagram first of all. The CCP arrangement means actually it indicates FCC, isn't it? Good. Okay. So this is actually FCC, but if you watch carefully, yeah, here you have the elements M and X. Okay. Here, these yellow small squares are there, no? They're all M. So where are M present? 2 places. Look here. These represent edges. So this is the edge center. 1, 2, 3, 4. They're present at the edge centers. Okay. And how many are there? 4. Also, it is present at the center of the body of the unit cell. So that is body center. Of course, you can have only 1 there. What about X? It's given as CCP arrangement of X. That means FCC. This is with respect to X. And FCC means we know X should be present at corners and face centers, right? Very good. And that's true. Look here. This pink circles or spheres, you can say. See, these are all corners 1, 2, 3, 4, 5, 6, 7, 8. And face centers, look here 1, 2, 3, 4, 5, 6, isn't it? Okay. If you know the contribution, we can easily go ahead. Right. What is the contribution made by the corner fellow? 1 by 8. So let me take white here. How many are there? 8. Therefore, 1 by 8 into 8 is 1. Plus, this is half is the contribution made into 6 equal to 3, right? Therefore, here you have 1 plus 3, that is 4. This is what? Number of X atoms. You got 4. Now let's look at, it is nothing but Q, okay? Q is 4 actually, right? Q is 4. M now, edge centers 4, body center 1. The contribution made by body centered atom is 1. 1 ones are 1, therefore it's 1 only. Plus the contribution made by edge center, just try to recall, it's 1 by 4. So 1 by 4 into 4 will be 1 again. This is also 1. Clear? 1 plus 1 is 2. That means here, look, P we got 2 and Q we got 4. That means, what is MPXQ now? So here we can write, no, MP, that is 2, and XQ, this is 4. Okay? But this is not the answer. Why? Because the question is not molecular formula. The question is empirical formula. And try to recall, guys, what is empirical formula? It's the simplest formula. Rather, it's a formula in which you have the simple whole number ratio of the atoms, correct, in that compound. Therefore, if you take the simple whole number ratio of both M and X, divide by 2, right? That's the simplest you can get. So this will be now 1 and this will be 2. So this is the empirical formula. So the right answer is this, not this. Okay, this is not the right answer. This is the right answer. This is the molecular formula. Once again, I'm telling you. Okay. This is the molecular formula, but this is the empirical formula. So this is the right answer. Therefore, where is the right answer? mx2. In other words, it is mx2. Okay. Where is it, my dear? B, right? Okay. Hope you enjoyed the session. The questions are very useful, I think. Please try some more to get better grip on the same topic because this topic is also equally important. Okay. Thanks for watching. Bye-bye.